Hello and welcome to this new section or this new lecture called Tensors. So previously we've talked about, we've done more of trying to understand the Einstein summation convention in dealing with tensors and vectors basically. Yeah. So now let's talk about tensors itself. Let's try to understand exactly what we mean when we refer to tensors. So basically, well, the world is very complex, right? So most objects can be defined by coordinate points. I mean, everything has, with reference to reference frame, you can describe an object. They could have like a vector coordinates. So what tensors can do, I mean, tensors have different definitions, but the very first one we'll be talking about is more like its transformation relation. But first of all, let's look at tensors from Wikipedia. So Wikipedia defines tensors as an algebraic object defines tensors as an algebraic object that describes a multilinear relationship between a set of algebraic objects related to a vector space. Right. So object that tensors map include vectors and scalars. So mapping is a very common thing that tensors are used to do, to map from one vector to another. I hope this gives some intuition into what we need to understand basically. And as can be seen from here, tensors can take different forms. I hope it's not too small to see on the text, but you could just, this is the source. You could just Google this in case it's difficult to see you, then you get the full stuff. So it can take different forms. So yeah, it can take different forms. Basically, I'll explain the different types of tensors subsequently. So, and tensors are very important in physics because they provide a concise mathematical framework for formulating and solving physics problems. So, you can usually find them in mechanics, that is for stress analysis, for elasticity, for fluid mechanics of solid, moments of inertia, electrodynamics, and different parts of engineering basically. So, it's very important for an engineer to have an understanding of what tensors are. Yeah. So if you look at the diagram, you see it's like this is a second order Cauchy stress tensor. Cauchy stress tensor basically, if you well, I assume if you're watching this video, you probably don't know what a Cauchy stress tensor is basically, but it's also a transformation tensor, right? Basically, these expressions are when you talk of mechanics of solids or so. That's why you would tend to encounter this or continuum mechanics. Hopefully, I should do some series of videos on continuum mechanics. Then the Cauchy stress tensor will be described to you. But you can see describing the stress at different points or so, or experienced at a material by a material. That's what the Cauchy stress tensor is. Basically, we have different kinds of stress tensor, from rotation tensor to even a zero tensor, and yeah. So as we progress, we get to have an idea and understanding of what the tensors are. So now let's look at this. Given that A, B, C, let's say A, B, C, and D are vectors, right? What I mean is when I write this, I simply mean A, B, C, and D belong to a class of vectors, right? So if we have a vector A and we have another vector B, they are different, right? A tensor T can transform from A to B. That transformation can be done by a tensor. Now, tensors are not only for transformation, but for this particular for this particular video, that's what we majorly look at: transformation and mapping. So a tensor transforms A into B. That's a vector into another vector, totally different vector, right? So that's what a tensor does. This is like, I can say, definition of tensor. Right. Yeah, Wikipedia gives a different, it says an algebraic object. Object here can mean a vector that describes an object that describes a multilinear relationship between set of algebraic objects related to a vector space, right? So objects that transform, that tensors may map, include vectors and scalars. So you see, we've mapped, it's like transform from A to B, or you mapped from one to the other. So these are the kind of things tensors can do. So these tensors have a linear property, or linear properties, yeah, two actually. So the first one, Number one, T is a tensor, A is a vector, in addition to another vector, will give you CA plus TB. Yes, you guessed right. You probably have seen this before. This is what they call the distributive property. Secondly, we have the associative property, which is we have a tensor and we have an arbitrary scalar and we have a vector, right? If you multiply this, it can still be the arbitrary scalar times the tensor times the vector, right? So A is an arbitrary scalar. The scalars can be like to reduce or increase in size of the vector, right? So this T acts as an agent. T acts as an agent of what? Linear transformation. So yeah, sorry, I think this alpha can act as an agent for stretching actually. Can stretch, right? Can either the vector stretch it, stretch, increase or reduce. Yeah. So basically, those are the two laws: the distributive property and the associative property of tensors. Now, tensors, we have the types of tensors. We have the zeroth tensor, zeroth order tensor, and zeroth order tensor. An example of this is alpha. I mean, this could be anything, right? Because all these are scalars. So this is zero. This is what we call zero order tensor. Zero tensor basically. Yeah. So sometimes you see a zero tensor written with a big O, right? Maybe it could be like a yeah, just consists of O zeros. You can have a first order tensor. An example of a first order tensor is a vector. So if this is A, right, it could be A1, A2, all the way to AN. This is a vector. So this is an example of a first order tensor. Second order tensor. Now, understanding what the second order tensor is basically, it's what these second order tensors are usually what we call tensors itself, right? Most often times when we refer to those tensors, we're referring to second order tensor. So for zeroth order tensors, they are called scalars. So more often you hear people mention scalars, vectors, and tensors, as opposed to zeroth order tensor, first order tensors, second order tensors. So basically, that's what that is. Now, your second order tensors are basically your matrices. Or let's see. Yeah, it could be anything. I mean, it could be T, it could be A, right? A equal to A, A11, A22, A33, right? So A1, 2, 3, A2, 2, 1, 3, A, 1, 2, 3, 3. What am I doing? Okay, sorry. A, 3, 3, 1, 2. So basically, this is a tensor. But more often than not, you call it a matrix, right? Now, a third order. Yeah, you guess right. You should be, and this is 3 by 3 matrix, right? 4 by 4. So tensors in practice or even in different forms, right? You can see tensors up to many or up to higher orders. It's not limited. There's no limit per se. In reality, in some mathematics problems, you can solve matrices that have like up to 1,000,000 by 1,000,000. Yeah, some still says a matrix, but that's a tensor. It's a tensor, right? So basically, tensors will not be something totally different from what you're already used to, but it's giving you an intuition of what it is, right? So if you usually hear a second order tensor, you're referring to a matrix. Now, basically, transformations are, I mean, we're talking of mapping, right? We have two vectors So the linear operation between them is mapping from one to the other by a tensor. So yeah, so if you have this T A equal to B, so what this means in essence is a first order tensor maps a first order. Okay, yeah, let me explain. Yeah, let me explain this first. So what this means, T is a second order tensor, A is a first order tensor based on what we just talked about, and B is a vector. This is a first order, right? If you multiply, it's the same thing as saying if you multiply a matrix times a vector, you get a vector, right? Good. So basically, what this just simply means is a second order tensor maps a first order tensor into a first order tensor, which is B. So second order tensor. Sorry, I'm handwriting. I hope to make it a bit legible. Maps a first order tensor into a first order tensor B. I hope that's clear. If you have two vectors multiplying each other, let's say A times B, right? If you multiply a vector by a vector, you should be getting a scalar. Let's say alpha, which is a scalar, right? Basically, a vector is first order tensor, is also a first order tensor, right? So basically what has just happened is simply a first order tensor maps another first order tensor into a zeroth order tensor alpha. I hope that's clear. So what just happens is the fact that a second order tensor maps a first order tensor into another first order tensor. This one, a first order tensor maps another first order tensor into a scalar. That's basically what that mapping is all about. Now, for a tensor, basically, tensor, it's a matrix. For instance, the simplest tensor we can talk of is a 3 by 3 matrix, right? Yeah. So, if we have, let me give an example of that. Let's say we have T equal to T11, T22, T33. Those are the entries on the diagonal. Then we have T21, 31, T12, T32, T13, T23, right? So those are the entries, or those are what they call the components, basically. So this is the tensor, and this is matrix of tensor T, and these are the components, which are 9 in number, right? Now, these components, basically, if you remember what I've said in a previous video, okay, that's related to vectors, basically, right? For a vector, a vector itself does not change, irrespective of the base vectors. It's invariant, but its components will change, right? Now, the components of a tensor depend on the base vectors used to describe the components. So let me write that down. The components of the base vectors. Sorry, component of a tensor, I think that's what I should write on the tensor depends on base vectors used to describe them. Now, if we use base vectors of EI, that is E1, E2, E3, to describe this tensor, then the components will be in that form, right? So if you have, these are the unit vectors. So unit vectors E1, E2, and E3 in the in the direction of, let's say we have three axes, right? Let's call them x1, x2, and x3 instance. So yeah. So what happens is under transformation, under transformation T, this should be plural. These vectors will now become TE1, TE2, and TE3. Now, look at, okay, sometimes it's very good to graphically visual understand this like this. Okay, so this is x1, x2, x3. Then we have a vector e1, e2, e3. So you see the unit vectors, look at unit vectors e1, e2 in the direction of the x1, x2, and x3 axis. They are in this direction, right? So under transformation, so if you have a matrix T or a tensor, sorry, tensor T, right? It's the same thing if it's a 3 by 3. So this T will become TE1, TE2, and TE3 under the transformation. So if you use T, if you apply T to each of this one, if you apply T to this one, you apply it to this unit vector, and apply it to this unit vector, they become this one becomes this, and this one becomes this under transformation. So what has happened is from E1 has become TE1 by virtue, okay, let's use TIEI by virtue of a tensor T. T has become has done a transformation in that. I hope that makes sense. Let me leave this a little more. Alright, so TEI equals to TJIEIEJ. Now, this expression explains what has just happened. This is the component, the new component. Actually, let me write here, because books wouldn't write it like that explicitly for you, but it will help you understand. This is the new component, right? That's the transformed. This is the old one, the old vector, old unit vector, and this is the matrix, right? That's done the transformation or the tensor. Let me stick with the word tensor, because even though it's a 3 by 3 matrix, but tensor is a tensor. That's the agent of transformation. I hope this makes sense to you. Now, if you have this TI, TJI, EJ, by now you should be able to expand this to give, this is a compact form, right? We should be able to expand this to give 3 equations or 3 expressions, compact form. Well, let me just quickly do that. 3E1, T, okay. Let's just go 1 plus T2 1E2 plus T3 1E3. You can verify this at your own time. I'm writing this very quickly. T1 2E1 plus T2 2E2 plus T3 2E3. That should be correct. Then TE3 should be T1 3E1 plus T2 3E2 plus T3 3E3. So these are the 3 expressions. Right. So you see this is very important. See this? I've expanded that to this 3 to give us this 3. Right. Now from these 3, from these 3 expressions, we can see this, right? T11 equal to E1 TE1 T12. Look at this. If you look at this one and this, see. So this is an obvious expression you can get from there. T12 equals to E1 dot TE2. Obviously, if you look at T21 again, you can simply pick out E2 dot TE1. So to get this component, to get this component of the matrix, the original in this direction times the transformed will give this. The original times the transformed in E2 direction gives this, like that. So you can do this for all the 9 entries. Or 9 terms. So what I'm just trying to say is that from these three, from star, this is obvious. From star, this is obvious, right? These expressions are obvious. If you look at this one, let's take a look at this. This is the component now. This is the old, or when I mean old, or the original vector, right? And this is its transformed component. That brings us back to this point. It brings us back to this point. See this? You see this, right? So this now can become Tij equals to Ei dot Tej, right? So if you take a look at this ones, let me change this color just to tell you that there's something different here. I'll take a look at this. You see it? You see? So there's some transformation. So basically, this Teij is the transformed component. This is the original, the entry, the new entry, right? So what this just says is that the components have been expressed with respect to a certain basis vectors. The basis vectors are the EIs, right, which is the E1, E2, and E3. So every tensor has to be expressed with respect to a basis vector. We use why, and one reason I know some people may have that question is why do we use unit vectors? For simplicity of the math. If you use more than that, you still get it, but it could be a bit, things will get complicated, especially if you're not so sure of what you need to do with your simplification. So these two expressions highlighted in green are very important, right? This expression, this one, you see, is the compact form. So this Tj is the original entry of the matrix, and this. So now if you look at how does these two relate, it's very simple. You can see Tji, right? And you can see Tji and Ej. So if this Tji, oh sorry, that's a mistake. Imagine if you probably try to do like some operations or so. This Tji here has become this Tji here has become Tij here, right? And if you look at that, Tij, Tji. Basically, it's like a transpose, right? So if you just play with your maths, like you're taking this one to this other side and bringing the other one to this other side and bringing this vector to this other side too, you get this. Does that make sense here? So basically, it's just simply about the maths, basically. So one more time, to get the components. To get the component of the vector, you multiply the entry of the vector, the entry times its times the unit vector. Then to get to get a transformed component right here exactly. But to get the component itself, you say the original vector times the old one. The dot product of that gives this. So if you just take some time to read through this, you should be able to understand exactly what I have done, basically. So if, for instance, let's take this as like, let me do like a numerical example. Numerical example this time. So if so we are required to obtain the matrix for the tensor T, which transforms the base vectors as follows. Okay, so make this TE1 equals to 5E1 plus 2E2, TE2, TE3, this. Maybe, okay, let's say 3E1 plus 4E3, so negative 2E1 plus 4E2 plus E3. Now, it says obtain the matrix T, right, which transforms the base vectors as follow. So what this we're just trying to do is we're looking for this T that's transformed EIs to TEIs. Now we've been given from this problem you can see we've been given the TEIs, right? It says obtain this. So what you're asking us to find is this T that was able to do from EI to this. This is quite simple, right? If you just look through, I mean, you just simply need to look. So to find this T, you see the TEI now has been expressed in this and this. So all you need to just do is just to look closely. 5EI right, TE2. So 5 in the EI direction, 2, 0. Because what we need terms from the EI, E2, and E3. For the second column, for TE2, we just need EI is 3. For E2, no entry 0. Because if you look at this here, there's no plus E2 0. Then for E3, we have 4. For TE3, we have minus 2, 4, and 0. So this is the transformed vector. So this transformed vector T was able to convert E terms E1, E2, and E3 into TE1, TE2, TE3. I hope that makes sense. Sorry, this is 1. This is 1, right? Because here is 1. Here is 1. I mean, it's not 0. I'm sorry for that. So that's basically that. So let's see a second example. So T transforms every vector into its mirror image with respect to a fixed plane. Just in case someone watches this later and is not sure, with respect to a fixed plane, right? T transformed every vector with respect to a fixed plane. So if E1 is normal, or it's a normal, and that should be decent to the reflection plane, what that means is that E2 and E3 are sort of parallel to this plane itself. We need to find a matrix of T. So the same thing like this, we are looking for the transformation matrix T, right? So let me explain graphically this. So this is the mirror. This T transforms every vector into its mirror image with respect to a fixed plane, right? So this is the mirror, this is it. We have E1, this is E2, and yeah. So this is the transformation this is another transformation, E2. This is into a mirror with respect to a fixed plane. If E1 is normal to the reflection plane, this is E1. This is the reflection plane here. Let me make this a bit bold. This is the reflection plane here. And E1 is normal to it. This is this. Oh, sorry, that's poor. E2 and E3 are parallel to this plane, right? E2 is this already, right? E2 is parallel to this plane. This is a reflection of that. Yeah. E3, I mean, this is a 2D example, right? So but we're assuming E3 is parallel to this plane. It says find the transformation that's made, for instance, E1 become E1 prime. See, C prime, it has moved, right? It has moved an angle. E2 has moved an angle too. So you're looking for. So now looking at this, normal to the plane is transformed. So when you have a vector, it's normal to the plane. If you are transforming by t, it will be transformed into a negative entry, a negative vector. But if the vector is positive, the vectors parallel to the plane are not changed or altered. Does that make sense? So look at this t. Since this t is normal to this plane, it's perpendicular to this plane, right? It becomes negative, this E1. So this E1 becomes negative. But since like E2, it's parallel to this plane, like look at this, it's sort of parallel, right? So, I mean, it goes not fully parallel, but it goes at this direction. This E2 does not change, right? So what happens is the transformation vectors now will be T. Basically, what you're supposed to look for is TE1, TE2, and yeah, even possibly TE3, even though it's a 2D example. So this TE1 becomes negative E1. TE2 remains itself, T3 remains itself. So this is something you should also note. Normal to the plane is transformed into a negative vector. But if the vectors are parallel to the plane, you see the plane we are talking of is this, right? It's a T transformed into a mirror image. You know, like a mirror image, if you transform this side, you see the other side, the reverse. That's why this, because especially when it's the normal to it, that's why we have negative of this, right? But if not, like this ones, it's unaltered, they're not altered. So now, let's write the transformation matrix. If you remember in the last example, what we simply did was we took, looking at this is minus E1, right? If you look at this plus 0E2 plus 0E3, they don't exist there, right? This is plus 0E3, there's no E1, right? So we write this out to be negative 1, 0, 0, 0, 1, 0, 0, 0. Oh, sorry, my writing is poor. 0, 0, 1. So this is the transformation matrix. Now we write this E with respect to this, trying to let people know that this is the base vector with which this transformation are taking place. I hope this makes sense. One final example. So if R corresponds to example 3, let's see. So R corresponds to a different okay, yeah, I'm thinking of an example that should make sense to. Okay, so R let me go with this. R goes with corresponds to a rotation of a rigid body about x3 axis by angle theta. Find matrix of R. So R yeah, let's do this. Yeah, I mean, you can still take this to be the third, x3, x1, x2. So R corresponds to rotation of a rigid body about axis, x3 axis, right? Yeah, rotation is about this axis, or this axis here, by angle theta. Find the rotation, find the matrix of R. R, it's a rotation matrix in this case, right? It's still the same as the T we've been using before. So basically, you're just simply asking what has converted EI to to REI, and it's simply an R. It's a rotation matrix. And basically, what the rotation matrix is, they simply, like, you change what you can see, right? If you have an object, you just simply change what you can see, but the object itself is not changed or transformed in any way. So the question gives this. So the question gives these parameters. Okay, I think I should have finished the question first. Oh dear. So let's say cos theta E1 plus sine theta. I guess you understand why we are seeing thetas and trig. Yeah, because it's a rotation, right? E2 should be negative sine theta E1 plus cos theta E2, then RE3. We are rotating about this, so we don't expect any change here. We don't expect this to change, right? Exactly. So we are rotating about this. We don't expect that to change. I hope this makes sense to you. So obviously these values have changed in one way or the other. Changed in one way or the other. Let me explain this. Let me see. Okay. So we have x1, x2, then e1 will lie on this, right? E2 will also lie on this unit vector. So this, if you rotate this at an angle theta, it becomes RE1, right? This rotated at an angle 2 becomes RE2. There's an angle here which is theta 2, right? But this 3, this is where we are rotating about. It says by about x3, x3. So that remains unchanged or untransformed. Does that make sense? I hope it does. So basically, just looking from these expressions, you can get R. You don't really need to solve anything. Just looking at it. Cos theta. So let's not forget, let me just write that. I love writing this for emphasis. So this is the transformed vector. It's been explained now with respect to, it's been moved by angle theta, right? So E1 has become RE1. Yeah. So its components, or the components of the transformed vector, the vector that did the transformation, will now become cos theta, which is this, sine theta, which is this, then 0 for the third axis. So sine theta and 0. Similarly for R2, RE2, it will be negative sine theta, cos theta, and 0. And for RE3, we have 0, 0, 1. EI. Trying to say that this is what this transformation was referred to, right? The axis which it was, it respect to the base axis. So I think this should be all for now. I hope this helps basically in trying to understand what tensors are. So basically, we just look at tensors as transformation, agents of transformation to transform from one vector to the other, right? So you can transform. Yeah, you could just read through this Wikipedia link to give you some more ideas, basically. But it's basically everything I've explained. You transform from A into B, That's from a vector. You transform a vector into another vector, and that's done by a tensor. If it's 3 by 3, it's a matrix. If it's greater than 3 by 3, like 4 by 4, 10 by 10, 1 million by 1 million, that's a tensor. And they have unique properties that they are distributive and they are associative as well. Then we basically at base level we have zero tensors, right? Zero tensors which are scalars. It could be like 1, 2, 3. Those are scalars, right? And they could be first order tensors which are vectors like this I've just explained. Second order, its matrices of 3 by 3. Then higher orders, then give the name tensors, right? Good. Then also like a mapping from one domain, from one vector to another vector. So we looked at it as saying that second order tensors map a first order tensor into a first order tensor into another first order tensor, which is B. And similarly, vector to vector to give a scalar. Then we looked at the components of this, and we try to express these components with respect to base vectors EI, right? So what happens when you transform one vector to another? When you transform EI to TEI, right? Exactly. So this was like a graphical explanation of that, trying to give an overview of that. Then I did some mathematical, well, I like to call them little jargon to try to explain, to show to you the components and how we moved from this point to this point, or to this point, basically. Then I did some numerical examples just to show to you that when we have it, you see, the funny thing is that if you look at the transformed component, it's more like a combination of the old, maybe of one axis and another, E1 and E2, right? You see them. Yeah, but you can with this TE1, TE2, and TE3, we can find the transformation vector itself that did like vector that was able to change from E1 to TE2. That's how we found that. And I just did other examples trying to explain to you that if you have a vector that is normal to the plane, if it's transformed, it's transformed to a negative. This mirror image transformed to the negative of it. That's negative, right? Yeah, and the negative is by the movement. It's by the movement, right? Negative vector. But if the vectors are parallel to the plane, it's altered. Then it's not altered at all. So that's why TE2 and TE3 did not change. Then we did with a rotation tensor. Rotation tensor will involve an angle. There's a movement, right? An angle. And we did the same analysis for that. I hope you find this video useful. Thanks for watching.